Hello and welcome to Pathways to Carbon Mitigation, UMass Amherst Roadmap presentation by myself, Ezra Small, and my colleagues Zac Bloom and Ted Mendoza. We're thankful for this opportunity to share our recent and ongoing efforts at UMass Amherst to decarbonize our campus energy system. I'm going to kick things off and provide some background information and context before Zac goes into the technical aspects of our plan, and then Ted will bring us home with an overview of our current master planning process and implementation. In 2019, Chancellor Kumble Subbaswamy released a letter which was his formal reaction to a combination of student advocacy and the work of our sustainability committee, which we've been calling the Chancellor's Charge. I'm not going to read this to you, but I'd like to highlight a few things. He established his intention for the university to be revolutionary, in line with the overall strategic mission of UMass Amherst. He also requested a study with a very focused question. What would it take to get to 100% reliance on renewable energy sources by 2025, or if that wasn't feasible, by 2030? He very specifically did not start with, can we afford it, but instead asked, what will it take? So today we're going to talk about how we went about answering this charge, what we've learned so far, and give you a preview of where we are heading. The Chancellor's Charge was given to the Carbon Mitigation Task Force, which I'll abbreviate to the CMTF. As you can see, the task force is made up of a diverse group of students, staff, and faculty. The CMTF selected a consultant team at the end of 2019 to help us develop the carbon mitigation study over the course of about a year. We assessed over 130 strategies, working with key stakeholders across the campus community and beyond. And we have made dozens of presentations to various groups, including capital planning, the budget office on campus, facilities, senior leadership, student groups such as MassPerg, utilities, and other state agencies. Before we dive into the results of this study, let's do a quick Energy System 101. UMass has over 280 buildings that need heating, cooling, and electricity to operate. That's roughly 13 million gross square feet. 70% of our energy, roughly 2 billion kBTU, is used for heating. We're a heating dominant campus because of our cold winters and lengthy shoulder seasons. So we currently use roughly 26 miles of pipes to distribute that steam heat across the campus. And we've been saying that that's a marathon of steam lines. We have a long history of providing the campus with reliable and efficient energy. Over the past decade, we have kept both energy demand and greenhouse gas emissions flat despite significant campus growth. So UMass has an important responsibility as the largest emitter of all state agencies in the Commonwealth at roughly 15%. Our campus emissions are almost all related to buildings, 98% building related, with most of it going to heating the campus, so that is something to keep in mind as we dive into our technology solutions with you. And we've kept our emissions flat, even with a substantial growth to our campus over the last decade or so. And we have exceeded the 2025 targets, but the challenge for us will be finding the emissions reductions needed to hit the state mandated target of 35% reductions by 2030 and 60% by 2040. And so the state looks to us to lead by example to fully decarbonize by 2050. A quick note is that what we're presenting here is really just scope 1 and 2 emissions. It does not include scope 3, such as commuting, food systems, and embodied carbon and waste systems. So just to do a quick history lesson, we've been through multiple energy transitions in our 158-year history. Our first transition was to a district energy system, and this began with our first steam plant in 1910 and expanded with our coal plant in 1918. In the 1950s, we added the ability to make our own electricity through cogen. This was a cutting-edge technology at the time. In the early 2000s, we began our next transition away from the 90-year-old coal plant to a state-of-the-art natural gas plant. The award-winning CHP was completed in 2009. This currently provides campus with an affordable, reliable source of steam and electricity with much lower GHG emissions than our previous system. So as we transition to renewable energy, our study has focused primarily on that steam distribution system, that marathon of pipes, some of which are now 100 years old. So since completion about a year ago of the study, it's provided a framework for us to understand what it would take for the campus to use 100% renewable energy. Though the study didn't provide a shovel-ready design or exact dollar figures, Ted's going to get into that a bit later, the study has rigorously assessed the phasing and overall costs of an energy transition. This is a starting point for the campus to imagine what it would take to become carbon neutral, and hopefully can be used as a resource and a tool for our campus leadership to work out what the next steps are to move this challenge forward. So when the chancellor gives you a bold charge, you try best to answer it. Is it possible to get to 100% reliance on renewable energy sources? We think the answer is no, but it might be theoretically possible, but it would take an impractical level of investment and disruption to the campus over the next 3 years. However, the study does outline a path to reach 80% reductions by 2030 and 100% by 2032. So there are five key takeaways for UMass Amherst that we need to do. We need to commit to transitioning away from steam as soon as possible. As long as we're burning fossil fuels, we can't have 100% renewable energy. So we need to move away from the combustion of fuels. We need to continue to accelerate energy efficiency work to prepare our buildings for this new energy system. We will continue to expand on-site solar, but we will have to procure more renewable electricity from the grid. Also, switching to a low temperature hot water system will unlock the potential for renewable thermal technologies on campus. And finally, it will take more than just pipes and solar panels. The energy transition presents a revolutionary opportunity for campus to use campus as a living lab for advancing sustainable education and research. Ted will also touch on this a bit later. So now over to Zac, who will dig a little bit more into our energy system now and what it will look like into the future.
Thanks, Ezra. So yeah, as Ezra kind of outlined there, there's been a transition about 3 separate times. And so let me set the stage a little bit for what's currently in the central heating plant. There's been a progression over time to create this microgrid to give more resiliency. And that started with, the on-site combustion and generation, but it's really progressed over time to, creating a transmission level service for electricity they need off the grid, but by and large, producing, the vast majority of their energy needs through that steam distribution system and on-site generation. So UMass has a handful of package boilers here that are kind of their backup as needed or supplementary, but the bulk of all the generation on site is coming from their own equipment, not from the grid. So UMass Amherst has the Herzig, the heat recovery steam generator, and all of these are really designed to run off of natural gas. Berkshire Gas, who does have the ability to curtail UMass Amherst up to 15 times a year, do so when the degree days are over 51. And so in those days, there is no ability to meet everything through natural gas. And so ultra low sulfur diesel will be used, but by and large, natural gas is the main fuel being used. And then the secondary fuel is the LNG. And if necessary, the ULSD will be used. But the UMass has already backed off quite a bit using ULSD over the past few years with the introduction of the LNG facility that started off as a temporary and is now permanent. And so if we go to the next slide here, we can really see exactly what it is that's being produced. So about 140 million kilowatt hours are used. About 100 million of those are produced on site, and the balance is really purchased from the grid or from the solar through a power purchase agreement that they have set up. So you can see over time, this has really changed, quite a bit. There's now on-site solar, about 4 megawatts. There's, at a parking canopy, there's also a distributed setup of solar on rooftops that equal 1 megawatt. And in addition to that transmission level, substation that was introduced, there was also some work as part of that to create a duct bank, which reconnected the east and the west side. So This allows a lot more control for the operators of the equipment, but importantly, it also serves as kind of the benchmark or the foundation for this large distributed low temperature hot water system, which is what we'll get into in a little bit more detail here. As they progress away from the steam distribution, which has already happened in a handful of kind of satellite locations or portions of the UMass Amherst campus. So what would be the benefit of modernizing this district energy system that's already state of the art? Even though it is one of the most efficient combined heat plants in New England, just the pure ability of using steam creates losses, both at the combustion from the fuel as well as the distribution through the steam system. So one of the biggest kind of outputs of a low temperature hot water transition is that it requires significantly less energy for the campus. And so even though the campus is growing, they can actually meet that with less source energy needs. It will also lower operational expenses quite a bit over time, as well as create a lot more thermal comfort. A lot of the buildings don't actually have air conditioning yet. And so in addition to the same square footage, being conditioned, there's also new things like air conditioning going into buildings that previously weren't. And so the last piece here, which once again, Ted's going to touch on is, the be revolutionary and how that integrates into the living lab and integrating into curriculum and getting faculty and staff and students to really understand and buy into this larger kind of roadmap. So this is the current system as discussed. The bulk of the supply, the fuel, is coming from natural gas. And then the balance, is imported grid electricity or on-site solar being generated. So all the gas is being used to create that thermal, as well as produce, about 100 million kilowatt hours a year. And so you can see in this existing system, we have the breakout of what is electricity, what's used for chilled water and what's used for steam. And the balance there that you can see, which is a really, really big portion, is energy loss. So that's everything from the combustion and the distribution losses. And so now when we think about the distribution, you can see that breakout of the energy loss, the heating, the cooling, and the electricity, as it makes its way through the system. And ultimately, the conversion losses. So this is a big piece in moving to a new setup for infrastructure on campus that not only uses less carbon, but requires less energy to be purchased or produced on site. And so you can really get rid of all that production and distribution and conversion loss, which ends up being about 50% of the source energy being wasted. And so if we think, what does that future district energy system look like? It's really envisioning this new setup where your combustion is significantly reduced. There's a low temperature hot water system, that moves energy around, which has much lower losses and can be used for, the chilled water and for the electricity. And because we're adding more square footage, as well as adding more air conditioning, there's a trade-off and kind of balancing act that needs to be, carefully considered. And so being able to actually add those spaces allows for better COP or better efficiency of the system at large. And so the end result here ends up being a demand that is growing, but is being met with less energy and less losses. And ultimately that equates to less operational, expenses, as well as less, maintenance on the system at large. And the final goal, which is reducing carbon. And so as we think about this energy transition recommendation, over the last decade, unless there's just a really, really warm winter, we've been at somewhere around 125,000 metric tons of greenhouse gas emissions. And so as Ezra laid out, in the beginning here, it is feasible by 2030. It's just not as likely unless there's really, really quick action to get all these projects moving. Because this is not a 1 year or 2 year or 3 year project. This is a multi-year effort from design, construction, permitting, as well as the labor force and equipment necessary. So what we're showing here is kind of a wedge chart that gives you that breakdown of all the things that could be done to get you there by 2030. And so what does that actually mean? What are the key takeaways here? The first is it is technically possible and commercially, available technology as of today. But to get to that transition, there needs to be aggressive action. And Ted will talk more about kind of how that's already progressing here. One of the other pieces here is that UMass Amherst, which is already the flagship campus of the UMass system, is set to be a leader in the Commonwealth and truly be, leading by example, not just in the classroom, but also in the environment and the community. And this will require, a cultural shift. As the chancellor said, be revolutionary. This is everything across the board, from educational research opportunities, as well as the leadership, on campus to get this larger cultural shift, moving, which will enable the campus to continue to progress both with technologies as well as legislative and regulatory needs. So with that, I would like to hand it over to Ted to talk about how UMass Amherst has already taken this larger plan and started to implement pieces of it to set them up to actually begin that larger shift.
Thanks a lot, Zach. So looking ahead, we decided that a multi-team approach was best, as seen here. Our core master planning group manages our overall efforts, and we've established 4 unique teams to focus on specific aspects of the campaign. Each team has a seat on the master planning group and communicates with each other as needed. We expect that the different teams will be in the spotlight at different times as our plan evolves over the next several years. Currently, our marketing team is in the spotlight, planning how our campaign is publicized to campus and the surrounding communities. Our business development team is evaluating financial strategies to inform the administration. And our Living Lab team is creating synergies with other like-minded groups on campus, many of which were formed prior to our own efforts. And finally, our facilities planning team is reshaping our stance on facilities projects to integrate them easily into the new carbon neutral system, and is managing our proof of concept RFP, which upon completion will backfeed to all the other teams for their own planning and decision-making. So building upon what the study told us, you can see here that we're focused on geothermal and low temperature hot water, because that's where we get the largest impact from our carbon neutrality analysis. As a comparison, our more recognizable renewable energy projects, several solar PV arrays and a renewable fuel boiler, only represent a minor contribution to our overall greenhouse gas reduction goals. An important point for us also is that we're not planning to buy many carbon offsets to achieve our goals. Thus, we're putting more weight on the successful implementation of this closed loop approach. Without its success, we would not be able to achieve carbon neutrality in a true sense. Now, our proof of concept scope looks at establishing this system between a head end on the west side of campus and a handful of buildings in the southwest region. There are 42 buildings included in our scope, compared to the almost 300 that make up our full main campus portfolio. The full RFP is to complete a schematic design with cost estimate of a fully functional new system, This includes a deep dive into each building to convert them from energy using systems into energy exchanging systems. This also looks at building envelope upgrades to minimize HVAC sizing and upfront investments. And more so, we're looking at ways to reuse our abandoned steam pathways to minimize trenching investments of the new underground piping. And since this proof of concept is a major endeavor in and of itself, optionally, we're also considering a reduced scope, meaning just looking at the geothermal analysis on the west side. This would answer the question, how much geothermal capacity do we need to support campus? So what does that reduced scope give us versus the full? The reduced scope gives us estimated geothermal capacity, but in addition, although we'll not look at each inside of each of the buildings, we can still figure out the building side demand, but it would likely be based on meter data and engineering assumptions. On the other hand, the full RFP would give us building side demand that's based on existing conditions, as-built systems, and detailed load calculations. And in addition, we gain lots of other knowledge seen here that is needed as we continue decarbonization across campus, including an establishment of our own campus-specific design standards for the new system. And we can now start to unitize the cost from our 42 building analysis and extrapolate it to the rest of our building portfolio. This more accurate estimate will help shape current and future projects so we can minimize lost investments and make well-informed decisions. Cost-wise, the full RFP is about 3 times the cost of the reduced scope. So outside of the obvious goal to divest from fossil fuels, our research so far has found that no campus of our size or type has yet completed decarbonization. So as a flagship campus for the state, and Massachusetts state being an energy leader for the nation, we're motivated to lead by example for society at large. Regarding state and federal funding, we understand that federal funding will likely be passed through the state, but will not yield much for the UMass system. Also, state politics will play a key role as both our governor and lieutenant governor are not seeking re-election. Alternately, we're exploring creative ways to establish funds and bonds, and maybe even offer carbon credits to build in-house capital. Currently, we're focused on developing ready-made narratives to position us for any of these future offerings. As a final point, we feel our management structure provides a unique approach to a task that we all eventually will have to face. Our multi-team collaboration empowers us to address the complexities of sustainability in real time and nurture a deeper commitment from us that is engaging and worthwhile. We believe this living, learning, and teaching approach positions UMass as a model for its occupants and others for years to come. If you have any questions, please feel free to reach out to us at the emails or phone numbers listed above. Thank you.